So here we have our random walkers moving around in 3 dimensions, taking a step of 1 in a random direction along the x-axis, the y-axis, or the z-axis, but never a combination of any of those. And we get these really neat patterns. A random walk in 3D is a really pretty thing to behold, and there's lots of neat math behind it too. We commented last time that a random walk in 2D will almost surely return to the origin at some point, but a random walk in 3D may or may not. In fact, if you go through the proof, and I have links to more details about this in the description below, but if you go through the proof, a random walk in 3D has about a 30-something% chance of returning to the origin. And we've already seen that in our animations that we've looked at, graphing the magnitude of the distance between the origin and the random walker here. Kramer actually did return to the origin, it looks like here, on about the second step. Josh has yet to return to the origin, and Kramer is pretty far from the origin at this point. And so we call this type of random walk a transient random walk, because you're really not guaranteed to get the random walker to return home. And in fact, one of the ways mathematicians have expressed this over the years is that a drunk human will eventually return home, but a drunk bird may never return home. Because you think about the difference between walking in 2D and walking in 3D. But seriously, folks, don't overdrink and lose your way home. But we can test this by creating lots and lots of random walkers. So that's what we've got set up here in our code for today. We still have the random direction in the X, Y, or Z axes. We have 200 random walkers that will be taking a total of 100,000 steps in 3 dimensions. We're going to keep track of whether these random walkers have returned home. So they all start out with a false value for home, for whether they returned home. And we will update their positions, calculate the distance between them and the origin, and if that distance is ever smaller than our tolerance value, basically if it's ever close enough to 0 to call it back home, then we will change their returned home value to true, and then at the end we'll count the number that returned home, divide that by the total number of walkers, multiply it by 100 to get a percentage, and we'll see whether we get a number that matches the prediction of 30-something%. I think it's 33 or 35. The last time I did this, I got 35%, so I'm pretty confident that this will work. So I'm going to hit Control-2 to run this simulation. We'll run this in fast motion. What you're going to see, though, is that we get some returning home here at the beginning, but after this point, there won't be very many that return home. So enjoy the fast motion animation. I will see you on the other side. All right, and there we have it. A return home rate of 36.5%, so right along with the mathematical prediction. You saw at the beginning we had some returning home, but then after about this point, there aren't any who return home. And again, the way to think about that is that when you're working in 3D, there's more space to wander around in than in 2D. So it's easier to sort of get lost, as it were, in 3D than it is in 2D. So that's nice that we have confirmed that mathematical result. I've got a couple more things to show you in this series. Next week, we're going to take a look at animating a random walk in 4 dimensions, and it's going to be fun to see how we can do that. So thank you so much for watching. I will see you next time. Bye-bye.